Hello everyone, myself Kirish with ANSYS tutorials on nonlinear analysis. So in nonlinearity, we have the different types of nonlinearities. Like here, I'll consider the material nonlinearity. Okay, so in that again, I'll choose the explicit dynamic analysis, and with that, we'll take the nonlinear material into account, and we'll run this UTM testing machine validation analysis. Well, let's start. So here you'll get the different types of analysis. You can choose the explicit dynamics analysis only, and you can just name it accordingly. Uh, the first step is to define the material. So by default it will take the standard material, that is structural steel. Now if you want to access the nonlinear materials, you can switch to the library. From there you will have the explicit materials, and there you will have the linear properties or non-linear properties actually. So you can choose the material, that is steel 1006, or you can choose any of the materials according to the standards. Okay, right now I'll take this material into account. Okay, so which has the non-linear material properties and even the non-linear properties accordingly, stress strain curves. Okay, the model, I'll use the same model which I have used it for the SolidWorks simulation as well, that is testing rod. So normally during graduation we did use the same thing. They will provide the rod that we need to use the universal testing machine. We need to fix both the ends, and we need to apply the displacement, and we'll note down the force value and the displacement value, and then we'll find out the stress results. Okay, and the displacement. So from that stress strain curve we'll find out. First thing, I'll mesh it. So while meshing, it is element order is linear. You can choose linear itself. I don't want the quadratic one here. And sizing, each and everything you can customize it. The quality, and here you could see it is coarse only. So minimum edge length, you can change it if you want. Okay, or else I'll just use the by default option. So you could see this is how it generates the linear mesh. The advanced technique, you can say by default in SolidWorks it is quadratic, remember that. Okay, the material definition, you can open the solid body. From there you have the assignment. So from here you can choose, that is steel 1006, the non-linear material. Okay, once you choose the material, now you need to define the boundary conditions. Let's say the explicit dynamic analysis boundary conditions. The first thing is support and the loading. Okay, so I'll fix this particular face. Okay, one, and I'll select these two faces into account, and I'll apply the fixture. You can even select the face only, so no issues, because practically you wanna just select the face, right? So like that you can define it. And then the actual displacement I'll apply. I won't apply the force over there, because I know if I just drag it up to 20 mm approximately, it's gonna break. Okay, along x direction. So this time I'll just select this face, and here I'll add the value, that is approximately 20, 20.1 or 20.2 you can select. Okay, so once you define it, you could see the direction as well. So it is along z direction positive. So once you define this much, from the solution you can choose the analysis type and initial conditions. Okay, so here you could see the end time. I need to define it. I'll define 0.01, and the maximum energy loss 0.01 I'll choose, or if you want to make changes you can make it. Initials time step, minimum time step, everything is program control. I'm not gonna take care of these things for now, because if it is like, if you're facing any errors, that time you can customize it accordingly. I'll just activate the results, that is by using solution tools. I need the plastic strain, equivalent stress, and if you want you can even activate the displacement. Okay, yep. So once you're done with this, you just need to run the analysis. It will take a certain time to just provide the results, because as this is the nonlinear analysis, the solver will take more time to just provide the results. From the solution output, you can activate the energy conservation plot, so that you can just have a look on how exactly the uh, analysis is going on with respect to the number of cycle versus strain energy. Okay, as you could see the curve formation. Comparatively, it might take 5 to 10 minutes to get the results, remember that. Okay, once this is done, you're gonna get the results, and then by using the results plot, solution plot, you can just same cross check the results. Okay, so here you could see it is 616.78 is the maximum ultimate failure stress, and the strain is 1.33 max. Okay, and at that location it is max. And now if you want to animate it, you can use the auto framing option. You can just set up the time frame, and you can play the animation. You could see how the necking gonna takes place, and once the necking comes into account, you already know the entire structure will collapse or fail at this location. Okay, the dimensions and all you need to define properly, like if you're building the new model into account. The deformation, you'll add it. You can cross check how much is the deformation has been taken into account. So I'll simply select this option, that is evaluate. You don't need to rerun the study, you'll get it. So 19.61, so we already know it is definitely gonna fail at 20 mm. Okay, so at 19.61 it forms the neck. So this is the displacement plot, and you can use the different types of plots by using these plot options, and then you can choose the contours like smooth contour, and we have the better visualization with this embedded with the practical model with deformation. Okay, let's say if you want to cross check the stress strain curve, so that also you can activate by using the plots. So you can just directly switch to the graph, and if I just use this one, you could see. So this is how the curve takes place, right? So first elastic region, and then plastic region, and then ultimate failure will occur. So this is how you need to carry out the nonlinear analysis. So we have taken the nonlinear material nonlinear into account, and we have run the analysis. And to deal with the dynamic analysis, explicit dynamic analysis, we have the separate module, that is explicit dynamics. So that solver or that workbench will help us to just deal with this kind of analysis. Well, that's all about this session. Thank you for supporting. Stay tuned.